And so, again, Flashback for our particle in 1D box, we used this to come up with the selection rules. We had assigned the symmetries of our wave functions using those definitions of even and odd functions. Then once we have the character table, we can assign those to particular rows, Millikan notations in the character table. We have the direct product tables that allow us to solve for the transition dipole moment symmetry, and we can determine if something's allowed or not. And so we can get these selection rules based upon the general case. All G to U transitions are allowed in this case because light is U. So if we have a G to a U, this U sort of cancels that U, and we end up with a G. Same with the other, going from U to G. So I should have swapped those and saying the same thing. And then for Raman, so the scattering selection rules, since our operator was Z squared in this case, then we have a G in the middle. And so we can't have a G and a U coupled because nothing would cancel the U. So we can either go from G to G or U to U by Raman. Now what that allows then is our selection rules to be 0, 2, 4, etc. And that 0 is Rayleigh scattering, and the changes in 2, 4, etc. are Raman scattering. So we want to apply this to the particle on a ring, the rotational wave functions. And notice in the 1D box, our wave functions are, our quantum numbers are positive integers. Because if we were to put negative numbers in there, nothing changes about the wave function. So we really wouldn't even be able to tell if there was a positive or negative quantum number in a particle in a box. Okay, it has no ramifications, no detectable difference. Even you would say, well, it's degenerate, but everything's doubled. And so that just puts a single factor in all of our probabilities. We wouldn't be able to detect it. So it wouldn't even change our normalized probabilities. So we wouldn't be able to detect if we had positive or negative quantum numbers in a particle in a box. We don't have a 0 quantum number in this case because there's that would zero out the wave function, and essentially you wouldn't be able to even do the Schrodinger equation on it. You have to have a non-zero result for it to be a normalized wave function. Okay, so not so for the particle on a ring. So this is our particle on a ring wave function. Not only is it imaginary here, that imaginary function, when you take into account Euler's relationship, brings in a real part and an imaginary part. And this is the motion around, this circle. It's what we call a rigid rotor because R is fixed. Well, and so you'll hear me talk about rigid rotor, and that's what I'm talking about. So this is the rigid rotor wave functions. And I just want to point out, what if n was negative? Okay, that would put a negative value up here in n. If we pull that out, it would be a minus I. And all that does in Euler's relationship is change the sign in front of the sine function. It doesn't change the sign in front of the cosine function. So the real part is unchanged, and the imaginary part changes. And so if we just sort of start here at 0, the cosine, so let's just plot this, the cosine would drop off and the sine would grow up, okay? But if we have a negative sign, then the sine's going down. It's actually coming in this way. So negative n, positive n. So this is real, and this is imaginary. So the relative position of the sine function relative to the cosine piece is the only thing that changes with negative quantum numbers. But we can say that they're not equal, right? The imaginary parts are different. And so there is a difference between a positive and negative rotational quantum number. Okay? It's not going to be a difference in energy, but it is going to be a difference in the wave function. Okay? So that means we have to keep the negative wave functions. Okay? And this has traditionally been understood as a difference between rotating clockwise versus counterclockwise. And so if we were to think about this going, say, cosine to sine, then back to negative cosine to negative sine, if we think of that as clockwise rotation, so like the maximum goes from cosine and then the maximum is sine and so on, then we would say this is rotating that direction. But if we take that same definition to say it goes from cosine to sine, and we're dealing with the negative quantum number, notice how it goes from cosine here. If we're rotating the other way, now sine's a maximum going in the other direction. You see how they're interpreting it as clockwise or counterclockwise? It's sort of going from maximum real to maximum imaginary. And let's say that that's the way we're rotating. Then if we switch the quantum number to a negative quantum number, then that sense of rotation goes the other direction, going from maximum real to maximum imaginary, then max negative real to max negative imaginary. And so if you were to plot those, sort of animate them, where you go from max real to max imaginary, you would see a rotation in one direction. If you flip that quantum number, then you would see rotation in the other direction. And so that's why we sort of talk about this as rotating clockwise or counterclockwise. Now, what about when n equals 0? When n equals 0, then the imaginary parts are gone, and the cosine piece becomes a constant. Okay? Because it yields a constant and not 0, then it's allowed. So we still have a quantum number 0 for rotation, but we don't have a quantum number 0 for the particle in a box. Okay, because at quantum number 0, we don't zero out our wave function like we do in the particle in a box. Okay, so these are our quantum numbers for rotation: 0, plus or minus 1, 2, 3, etc. Is there anybody want clarification on this? Ask now. Yes.
Just one thing. On the equation, are you still multiplying 1/2 pi into?
Yes, thank you. Yeah. So we still have this whole thing. 1/2 pi. Yeah, very good. And so here's various ways to depict the particle on a ring wave functions. And so we'll go ahead and put the 1/2 pi in front. Again, that's our normalization constant. And one of the restrictions on the wave function for rotational motion is that these areas have to match. Now, I've plotted it from minus 180 to 180. A lot of times people plot 0 to 360, but I like to see everything centered in the middle, okay, around 0, so we can determine, things like even and odd functions and so on. Okay, so this has set up the restriction on those integer multiples of pi, because again, this has to go all the way down and match up where it's going to be on the other side. Otherwise, we have a problem with our wave functions. So if our quantum numbers were not integers, it would look like this. Let me think about how to plot this. So let's say we had a wave function that was, say, 0.75 for our quantum number. Okay. Let's see. Let's do that. So it's coming down and it doesn't quite make it down, and it matches here and it matches there. Okay, so it matches left and right, but notice that as I get to this point, what happens? There's a sharp point. Do you know what rule that fails in terms of our quantum number? I mean, our wave function rules. The function is continuous. The function is single valued. But the first derivative, yeah, it doesn't have a continuous first derivative. Because at that point, I get two answers for my first derivative. If I'm taking the slope from this side, so I'm calculating the slope, and I get to this point, the slope is that direction, right? Or that value, so it's negative. If I'm calculating the slope this way, it's a positive slope. So at that point, my first derivative is discontinuous, okay? Because I've got a negative slope and a positive slope. If I were to plot the first derivative of this function, it would be broken there. And so we can't do the Schrodinger equation on this wave function if our quantum numbers are not integers. Okay. And then we explain why the positive and negative, that just changes the sign in front of the sign function. Now, since this is a rotating system, we could take this 180 and join it to the minus 180, and we end up with this piece right here. So let's go ahead and set this side right here equal to 0, right? And this is 90. This is 180. Okay, all the way around. Or we could have done it a different way. But do you see how this plot right here is this plot? Yeah. Or let's change this. Let's make this n 0. Because that's greater than 1, right? And this 180. So we start out at this piece right here at 90. We cross 0. At 180, we're at its the most negative piece. You see how this cosine function then gives us this shape? Everybody see that? Okay. Now, what if we were to look at this from the top down? Let's draw a line for this node right here. So there's a node right there where the wave function's not changing. And this piece is positive, this piece is negative. All of these values are negative, and these pieces are positive here. And so that's what's being shown here. The positive and negative signs are switched, but it's not really that important. So we have this positive piece, this negative piece. So can everybody see this as the same wave function? So I'm just trying to show you all the different ways we represent these wave functions. Let's look at the n equals 2. Okay, so that one is going to be this pink one. It goes down at 90 degrees, it's negative. At 180 degrees, it's positive again. And so we'll start here at 0. At 90 degrees, it's negative. At 180 degrees, it's positive. It's got two nodes that cut across this way. It's so hard to do on this tablet. Okay. And so we have a positive here, negative, positive, negative. And you can see that plotted here. Because we're going to start using these little wedges, these little pies with slices that are positive and negative, and that's how I'm going to be representing these wave functions. And so I just want you to be able to look at those and say, okay, I see what's going on with those. This one's n equals 3, where we have 3 nodes, and it gets really difficult to draw them. Okay, there's one, this one through the middle, this one diagonally the other way. And we have positive, negative, positive, negative. And you see from the top down, we have those 6 pieces. Now let's look at these. Can we figure out the symmetries of them, at least G and U? G, U symmetry. So remember, G's and U's are given by the inversion operator. So if we invert these wave functions, what do we see? This is why it's really nice to look at these top-down images, because you can see inversion really well. And so let's look the bottom one. If I take a point anywhere on this wave function and invert it through the center of mass, I end up on the other side and it's still positive. And so this one's going to be G. If I take a spot on this wave function, go through the center, and go to the other side, it's the opposite sign. And so that's U. Here the positives are opposite of each other, the negatives are opposite of each other, so that's G. And here the positive is opposite of a negative, so that's going to be U. So you should be able to just look to see if what's on the opposite side. If it's opposite sign, it's U. If it's the same sign, it's G. Pretty easy, yes?
So you actually don't have to draw it out, you can just look at the...
Yeah, you could just look at those. You could look at the numbers too, yeah. Okay, now this one, n equals 0, that's a plus or minus. I mean, there's no plus or minus there. So this is a singly degenerate energy level or wave function. And so it's going to be an A, okay, or a B or what have you. It's going to be one of those, either A or B. But then this one is doubly degenerate. So it's going to be an E something. This one's doubly degenerate, so it's going to be E. So we can know from our knowledge of character tables what kind of symmetry species or Mulliken notations these various wave functions are going to be. If they're doubly degenerate, they're going to be E. If they're singly degenerate, they're going to be A or B, something like that. Okay. So now let's think about this ring and maybe even go through the flow chart with it. Okay, so if we look at the flow chart, does anybody have one handy? Okay, very good. So what's that first question? Pardon? Yes. On Otterbein, this may be why they changed that on Otterbein. Okay. So let's go. Let me change this. And let's go to the display capture and look. Otterbein. And it's the symmetry challenge, right? And so let's just pick, we'll pick a linear molecule. But anyway, does this molecule have an infinite rotation axis? That's a better question, I think, than linear. Yeah, you know, and they changed it. So my flow chart was just always focusing on molecules, but really we're trying to grab the symmetry. And so it's asking, does it have an infinite rotation axis? So let's go back to our flow chart here. And infinite rotation axis, does our ring system have an infinite rotation axis? Yes, the z-axis is an infinite rotation axis. C infinity. Okay. And then so then we get over to the say yes to that, and then what do we have the next question?
Does the molecule contain an inversion center?
An inversion center, yes. And so our ring system, there's no change in potential energy around this. There's nothing, no features of our ring that would make it not have an inversion center. So we go over to the other side, it definitely has an inversion center. And so what is the result for our point group is d infinity h. Yeah, so you know, we had, in terms of our paper, we had to justify what point group are we going to call the rigid rotor, because it's not really a molecule. I mean, we're looking at the symmetry of the system as a system, and it's a particle on a ring. It's this ring. What is this ring going to be? It's got a C infinity rotation axis. It has an inversion center, and so therefore it's d infinity h, even though it's not a linear molecule. It's not like CO2. Okay. And so that's where we end up with this d infinity h character table. Now for our paper, we had to actually expand this table. If you look at the ones that are given, it typically goes to E2G and E2U and didn't continue on. But we started looking at specifically this particular rotational symmetry column, and we realized that this quantum number here is giving us right there the wave functions, 2, 3, 4, all the way up to n. And then whether it's G or U under inversion will tell us whether it's an E1U or an E1G, E2U or E2G. And so we end up with this particular row, essentially, whatever our quantum number is. If it's an even number, it's ENG. If it's an odd number, it's ENU. And then we have XY polarized light is E1U. So we can come up with our selection rules using this. So we can come over here and we can assign our quantum numbers. The first one, again, is A1G. But the second one here, n equals plus or minus 1, it is U because of the inversion center. And it's E1 because it's state number 1. So this 1 goes right there. And the U we get from looking at the symmetry of the wave function. And then the next one is going to be E2, and it's a G. And then E3, U, E4, G, E5, U, E6, G. And on and on and on, okay, as we go. And so that's a good place to stop. We've assigned the symmetries and the point group character table for all our wave functions. And next time we'll determine the symmetry selection rules. Okay. And then it's easy to do the selection rules for particular cases. It's more challenging to do the general case, to try to understand what are all of the possible combinations going to be. Okay. For the particle in a box, it was easy because we saw that GU transitions allowed all of the odd transitions to occur. So we could go from 1 to 3 and 2 to 4 and 5 to 6, 1 to 2, 2 to 3, 3 to 4. But in this case, our rotational selection rules are incredibly restricted. It's only delta J plus or minus 1, or delta N plus or minus 1. And we've got to figure out why that is. So that's an unusually restricted selection rule. So we'll look into that more next time.